All right, everyone. Thank you very much. I hope you had a nice rested coffee break, and I hope you use the coffee breaks not just to refresh yourself, but also to network and to meet all the experts and people interested on the theme of artificial intelligence, policy, and business. So thank you very much. We're going to be moving on to theme B, which is quite an exciting one. This one is looking at the implementation of artificial intelligence within firms and measuring the reorganizational effect around this. The first presentation is going to be by Iavor Bojinov, who's from Harvard Business School, and he's going to present a paper on nailing prediction, experimental evidence, and the value of tools in predictive model development. So really looking at within the firm and the accuracy of these type of predictive models that was previously discussed by Avi Goldfarb. And then after him is going to be Jonathan Timmis. We had to make a slight moderation to the agenda because one of our previous speakers couldn't make it. So John will be stepping in and giving a presentation on the effects of capital incentives on cloud adoption, big data, and the diffusion of artificial intelligence. So thank you for coming back to this event. Let's welcome people online as well to participate, and I please encourage everyone to actively engage in questioning and answering throughout. Thank you very much.
All right, thank you so much. You guys can hear me? Great. Thank you so much for that introduction, and thank you so much for putting on this amazing event. I've had a blast so far this morning, and I'm excited for the sessions after that. So with this talk, I'm going to sort of flip things around. I think in the past, people have really focused on looking at sort of the consumption of machine learning and AI. So a lot of the talks we've heard have really been around, are companies doing this? Are companies sort of using AI? Are they leveraging? But here we're going to flip things around and we're going to focus on, well, how do you build these algorithms? How do you build them effectively? And in particular, what we're going to try to do is actually study the people who develop the algorithms. So we're going to flip that perspective. So, just to highlight, this is joint work with Daniel Yi, who's going to be on the job market next year. So if you're a faculty and you're going to be recruiting, look out for him. He's amazing. And then the other student is Paul Hamilton, he's only a first-year student, so he's got a few more years before you can steal him away. All right, so as we've seen, AI is highly visible. It is almost everywhere we look, right? So if we pull up online and we pull up a news article, we'll probably see some sort of screenshot of something like this, which is ChatGPT, the fastest growing app of all time. So it sort of gives this illusion that maybe algorithms really are absolutely everywhere and they're touching pretty much everything we're doing. So here, for example, is Netflix. Who has Netflix? Pretty much every person in the audience has Netflix. Well, if you have Netflix and if you regularly use it, then you're probably subject to one of their many different algorithms, which determines essentially what you end up watching. It determines whether you watch more movies, whether you watch more TV, etc. But what we've heard already this morning is that maybe the distribution of AI is not uniform. It's not across all tasks and all businesses. And in particular, here I just have just a simple screen grab from the 2021 AI Index report. And as you can see here, we basically have the different functions in the different industries. And this is just looking at sort of AI adoption within those. And as you can see, it really is not uniform. So even in areas where in one particular, in industries where there is really high level of adoption for one particular function, there may not be high levels of adoption for other functions. And this kind of led us to ask this question, right? Like, how can AI be so unevenly implemented across businesses if the technology that is underlining this is public knowledge, right? Like, this is all built on, typically on open source libraries, using machine learning methods that have been written in academic papers that we can all just pick up and we can read, and we should be able to implement. Now, if we look for an answer to this, we can sort of go back around 10 years, and the prevailing idea was that the thing that explains this is worker skills, right? We need workers that are able to implement this. Not every single person can just pick up a machine learning NeurIPS paper and go to their laptop and actually implement this and start driving value. Okay, so we thought, okay, maybe that's true, skills are, of course, really, really important. And then what's happened in the past 10 years is that the number of people with the necessary skills to implement AI and machine learning has rapidly grown. And we've seen this in some of the talks earlier. And the demand for these skills has also gone up. So maybe this should lead to some sort of leveling out, but we still haven't seen that. And the other thing that's also really interesting and got us to wonder is, in addition to these skills and these technologies, there's been this really large growth in the prevalence of tools. And what I mean by tools is basically an implementation of a methodology. A methodology is a conceptual idea, and a tool is an implementation of that conceptual idea. And here, it got us to thinking, why are there so many different tools? If this technology is public knowledge, you should all be able to implement it. Why are there so many tools designed to actually implement this methodology? And here I just have some examples of it. On the left, we have like the cloud infrastructure. Each cloud provider has their own machine learning frameworks. And then in addition to that, there's a lot of open source machine learning software libraries, things like Python packages like sklearn, PyTorch, Hugging Face for NLP and for LLMs. And then in addition to that, companies also build their own internal set of tools. And these tools tend to be wrappers for essentially open source technologies and packages. So just to make things really concrete, let me just walk you through an example from LinkedIn. So this is LinkedIn's Pro ML workspace. This is from their blog. I forgot to put a link on there, but it's all public knowledge. I'm not disclosing anything. So this is basically an integrated platform for rapid AI development and deployment, and it allows you to do several different things. It allows you to generate data and feature engineering. It allows you to offer, train, and evaluate models. It even allows you to experiment with these models on real customers, and then it allows you to actually deploy them, and then eventually to even monitor their health. And the whole point of me showing you this, and here are just some screenshots, is again to sort of emphasize, right, if it was really just the technology and the skills, you wouldn't see these types of tools becoming so prevalent, right? These tools are basically implementations of these methodologies. So this led us to the following question. What is the effect of tooling on predictive model development, and how does its effect compare to the effect of the methodology on predictive model development? So what we're going to try to do for this first question is we're going to decouple technology into the methodology, which is the conceptual ideas, and tools, which were the actual implementations of that methodology. Okay? And why is that useful for us? Well, it's going to help us understand, hopefully, why we're seeing some of these differences in algorithmic developments, and it will give us a better sense of what actually leads to AI and ML development, not just the consumption of it. The second thing we're going to look at and try to answer is, how does tooling interact with skills? Right? Are tools and skills complementary, or are they substitutes? And that's really important because we already know skills are really important. So what is that interplay between skills and the tools and the methodologies? Now, I'm going to define everything formally in a little bit, but I just wanted to give you a sense of where we're going. So how are we going to try to answer this? Well, I love to run experiments. So my first idea was, let's just run an experiment. And that's exactly what we did. So we ran a real-world machine learning prediction competition that leveraged Kaggle and allowed us basically to take a bunch of we focused mostly on students, but a lot of them sort of had work experience. I'll tell you a little bit more about the population in a moment. And we basically removed access to advanced machine learning libraries. And you might be thinking, okay, why did you do that? Well, it turns out it's really hard to build new tools, but it's much easier to just take away access to tools, right? And if we do 1-, that gives us a sense of what the effect of tools is. Okay, so here's a quick outline of what I'm going to do. I'm going to spend a little bit of time just talking about the conceptual framework that we're engaging with. Then I'll give you some more details about the experiment that we designed. And then finally, I'll share some of the results and the implications of the results that we've seen. So the conceptual framework is, let me just take a step back and think about the steps that a typical machine learning project goes through. The way I like to think about it is there are 5 stages in a typical project. The first one is the selection. This is about the prioritization and the effective sequencing of an idea. The second one is the development. This is the actual model building exercise. The third step is the evaluation. This is the experimentation, the A/B testing. This is trying this model out in the real world to see, does it actually work? The fourth step is the actual deployment. This is the release and scaling of the algorithm. And the final step is the management. This is sort of the continuous monitoring, improvement, etc. And I think it's useful to separate all of these steps because very often when you're looking externally from a company and you ask questions around, and we were talking about this offline during the break, right? When you start to ask questions around, are you using AI? The impact of the AI and the machine learning will depend on what stage you've got in it, right? You could be using AI where you're just doing some basic experimentation and you haven't done wide-scale deployment, right? So it could look like you're actually underestimating the impact of these technologies. So I think that's something that we're going to see that's going to change over time. All right, so in this talk, I'm just going to focus on the development, and because Avi's here, I'd like to take, well, he left the room for this, but that's fine. In spirit, he's with us. And he's got this wonderful book on the prediction machine, and now he has the new book as well. And really, what we're going to be looking at, right, what are the drivers of predictive model development? And if you look at his book, and if you look at a lot of other books and articles, people typically say there are 3 things that drive product development, predictive model development: data, compute, and models. Data is how an empirical reality is represented. Compute is how computational resources are structured and employed. And models are how models are structured so as to capture empirical realities in the data. And this is what people usually say, okay, if you want to improve machine learning, you have to either improve data, compute, models. But what we're suggesting is there's an additional dimension to this matrix. And the first hint of this is, of course, this older literature on the use and the value of skills in the impact of technology. So as I mentioned already, and here is sort of the formal definition, we're going to take this technology and we're going to break it up. And again, just to underscore, I think these definitions are quite important to understand. What we're saying is the methodology is basically the abstract conceptual knowledge of how to solve a problem. Think of this as like a paper that someone wrote, right? That doesn't mean that you'll be able to leverage it. It just means there is some solution that you can read about. That's the conceptual methodology. The tooling then is the implementation of this methodology, and this could be a combination of hardware and software. So if we come back to this picture, here's a couple of examples of what the methodology looks like for data compute models. So for example, for data, it could be the split, apply, combine framework. It could be one hot encoding, or it could just simply be more observations, right? That's a sort of another conceptual idea within data. For compute, it could be things like the backpropagation algorithm, or just acceleration through GPUs, TPUs, etc. And then for models, this is the thing we're all familiar with. This is your regression models. It's your random forest. It's your BERT if you're looking for large language models, etc. Then the tools, just to give you some more specific example, this is things like R's dplyr, Python's Panda, PostSQL, and then for the computing, it's things like PyTorch, etc. And then for the models, it's things like sklearn, Hugging Face transformers, AWS SageMaker, etc. These are all examples of tools. So what we're going to aim to do in this project is we're going to focus on comparing the access to tools relative to the methodology when it comes to sort of more observations, because it turns out it's really hard to remove people's knowledge, so we can't do that. And it's really hard to give people new knowledge, so we're not going to do that. So we're going to try to do the simple comparison, but in particular, we're going to really, really focus on this value of tools just to give us a sense of how important they are. And of course, the skills, they're going to be really critical. And in particular, we're going to actually differentiate between 2 different types of skills. We're going to define general skills, which is basically your ability to solve a data science problem. And we're going to also assume that people have this sort of either data, domain, computing, or model-specific skills. And this is going to be really interesting because it's going to turn out that the impact of tools is going to be different when you interacted with the different types of skills that I'm introducing here. So more on that later. Okay, so just to give you a quick takeaway for our results. So for our first research question, we're going to show that the restricted access leads to a log-log score drop by about 30%. So that's a huge economical and huge statistically significant result, which hopefully isn't that surprising. The second thing we're going to be able to show is that this is roughly equivalent to reducing the training data set size to 10 to 15% of its starting point. So that means if you have 100 data points, the impact that you'll see is equivalent to using, say, 10 data points to train your models, right? That's a huge loss, like a huge meaningful loss. Then for the second question, what we're going to show is that it turns out tooling does not interact with an aggregated measure of skill, which is really surprising. It basically means that if you're high skill or low skill, the effects of tools is kind of the same. But things get really interesting for specific and for general skills. So we're going to show that tools are actually complementary to specific skills, but they're actually substitutes to general skills. And this is going to suggest that there's some sort of mechanism at play that allows tools to encode general skills, and it sort of changes the type of skills we need to develop effective models. So I'm going to get really specific about this in a moment. All right, so let me tell you about the actual experiment that we ran. So what we did was we basically ran 2 parallel Kaggle competitions. So for whoever's not familiar with this, this is basically a website where you can put a holdout data set and then people can upload their predictions and then you give them a score on how accurate those predictions are. We're going to basically get all of our participants to complete a prediction task, which is going to be a simple binary prediction task, and I'll tell you a little bit more about that in a moment. And then our treatment, again, I'll tell you even more about it, is we're going to restrict access to advanced implementations of advanced machine learning methodology. So we're going to block things like random forests, gradient boosting, neural networks. But we're not going to block their ability to write their own random forest function. We're just going to block the ability to use the tool that implements it. And of course, no surprise, no one actually tried to implement it themselves. But I was joking actually with people earlier that, okay, maybe with generative AI, our result is going to have to be thrown out of the window because now I can go to ChatGPT and say, give me the Python code for building a random forest. And we're actually running a follow-up experiment to see if that is actually true. I don't have any results on that yet, but I am aware of this. So if that was your question, yes. Great question. That means you're listening and thinking. All right, so let me tell you a little bit about the recruitment and the randomization. So we basically focused on basically leading US universities, and we recruited around 400 teams. Teams could be pairs or individuals. Most people chose to do it in pairs because it's more fun to work with someone else. And we got about 400 people sort of signing up initially. When it came to game day, of course, a bunch of those people didn't actually follow through. And we had about 122 that started our Qualtrics survey, which is where people would input their background and skills, et cetera. So you can imagine this is the information we're going to use for our skills measures. So then what we did was, as they completed their Qualtrics, we just did a simple Bernoulli randomization. So we would just flip an independent coin, and with probability of half, you'd be assigned to the restricted group, and then with probability of half, you'd be assigned to the unrestricted group. So of the 122 teams that started, we had 61 and 61 in each of our groups. And then what happened was we required each team to make a submission to Kaggle and also to submit their Jupyter notebook with all of their workings. I'll give you more details about that in a second. And we had, as you probably expect, a little bit of a dropout. What's really interesting is we did a ton of analysis on this, and there was nothing systematic about the dropout. There was none of our observed covariates were predictive of who would drop out. And you might be thinking, oh, if I went onto this prediction competition and you had the restriction, I should be dropping out at a higher rate. But we didn't see that. We actually saw that people in the unrestricted class were dropping out at a higher rate. So, we did everything we possibly could to try to predict who would drop out. And there just really was no information, so we were going to treat this as missing completely at random and kind of ignore it for our analysis. But again, in the paper, there's lots of tables to justify this claim. I have some in the appendix. I don't think I'll have time to show you those. Okay, so the prediction task was taken from this Tarifi's pump repair, which is basically this really interesting data set that has a ton of different water pumps in Tanzania. And it has a lot of information on those water pumps. It tells you where they are, what type they are, who set them up, when they set them up, and so on and so forth. It even has the exact location, the altitude, etc. So really, really rich data set. And the task is very simple to predict, is this pump broken or is it fine? And of course, this is a really business relevant problem, right? We do this all the time in predictive maintenance. We want to figure out where should we send our people so that we're not wasting resources. This is the exact example that Avi gave around trying to figure out which pumps should we dig out, right? That's a very simple binary prediction problem that could be formulated in exactly this way. So it's a very generalizable problem that people are solving. The treatment, as I mentioned, is we removed access to advanced machine learning implementations, but we allowed them to use constrained generalized linear models. So think logistic linear regression, or constrained versions of it like lasso, elastic net, etc. So all of that was fair game. They could use that. The thing we didn't do, of course, is we explicitly said you can use any of these methods, you have to implement them yourself. And then the other thing we said was you can use any function from those packages that is not a modeling function. So like scikit-learn, for example, has some really good functions around doing test train splits, etc., which are just useful from a modeling perspective and automate some annoying tasks. So we allow them to actually do that. And you might be wondering, okay, surely no one complied with this. We actually had 100% compliance, and we did automatic checks to make sure that everyone were complying, because what we did was we actually got everyone to use our custom-built Jupyter notebooks, which were through Colab. So I'm probably throwing a bunch of words that you don't know. If you're not familiar with Jupyter Notebooks, it's basically like a really nice graphical interface of coding and text, etc. It's really, really popular with data scientists today. And Google has an implementation. And what this does is it actually records diffs every 15 seconds. So we got this crazy rich data set of everything that every person was doing as they were developing these algorithms. So I think this is probably, as far as I know, the richest data set on algorithmic development to date. And of course, we have the Qualtrics survey, which is all of the background information. And then we have the Kaggle, which is the actual results. And that's really what we're going to be using for our sort of final measures. OK, so there's two really primary outcomes. Of course, we have the treatment, which is just a dummy, whether you are unrestricted or restricted. And then our primary outcome is we're going to renormalize things, basically. So they're on this really simple 1 to 0 scale, which says 1 is like our best performer, and 0 is our baseline. Baseline is basically I put in the averages. I did no prediction. I just put in the averages. And 1 is, like, that is the person who did the best in the competition, has a 1, and then everyone is scaled between that. And this is just for simplicity of interpretation. One thing, actually, I probably mentioned, but I didn't make it crystal clear. We made sure in the randomization that the two groups, although they knew that there were two different versions, they had no idea what the rules were, and they had no way of communicating with anyone that was in treatment or control, and they could not see how those two groups were faring, and we had completely separate prices for those. So there was no interference across the two different groups, so we don't have to worry about that. OK, so as I mentioned, we have the additional data, and it lets us do really cool things, like figure out where people spend their time, how the intervention changed people's focus, and I won't really have time to talk about this, but if you have interesting ideas of what we might want to do with this data, please come and speak to me at lunch or throughout the day, because I think we've just even started scratching the surface of this. Anyway, so let me give you some of the main results. So first, just to give you a sense of who we had in the study, it was people who graduated between 2016 and 2022, because we opened it up to alumni. People with undergraduates, masters, PhDs all participated. We had people from data science background, from physical science or engineering, social science, so a pretty broad representation. And then the thing that actually gave me a lot of hope in terms of generalizability of these results is that actually a good chunk of our participants either had worked full-time as a data scientist, or they had done some sort of internship. So I think, of course, this is not a super representative sample, so I'm not going to try to say this is going to hold for everyone, but I think it gives us some sense that some of these results may be a little bit generalizable. And we had a pretty good balance between men and women as well, which I thought was quite nice. Okay, so let's focus on question 1. And we did a ton of different analysis, and let me just start off with just a density plot of the results. So remember, the score is, if it's 1, it means they did really, really well, and if it's 0, it means they did pretty poorly. And you can see the unrestricted class, which is the purple one, is sort of much more skewed towards 1, right? Those people tended to perform much better, whereas the restricted class is sort of skewed separate. And you can see there's this like bimodal distribution, which basically makes sense because some people tended to be better than others, and this is basically a distribution in skills. That's what we're seeing here. So we can do, this is where the 30% comes from, so we can do a basic regression, which is equivalent of just doing a t-test, right? So it's very straightforward. And we can see that the effect of being unrestricted is this 30%. That's the number I was giving you earlier. And we can include whatever covariates we want in there. Here I just gave you just a couple of examples. It doesn't really change our effect size. So this is very robust to putting in all of the measurable covariates that we have, or none of them, and we did balance checks. They were all actually perfectly balanced, so you wouldn't expect this, but again, this result is very robust to this. And of course, we can do non-parametric results, so we can do like a Kolmogorov-Smirnov test to see if the distributions are equal, they're not. We can do t-tests, etc. So we basically can do, for whatever statistics you want, the result stands up to it. Now, the next thing I want to show you, and this I think is really clever what we did here, and basically, because we have everyone's code, we can rerun their models with less and less training data. So we can take the winners of the 2 competitions, and we can gradually retrain their model, say using 90% of the training data, 80%, so on, until we get all the way down to 0. And that's how you end up getting these curves. And what you can see is that unrestricted class, when it went down to about 15% of the training data, it performed as well as the restricted class best person. And then the average treatment effect, it will go down to sort of the average was 10%, which is where we get that 10 to 15% number. So that gives us a sense of how important these tools are relative to just the simple answer of let's get more data, right? Traditionally, if you're thinking through that framework, the data compute model, you would have said, oh yeah, just get more data, that will fix everything. But it turns out you actually need the tools. That's the thing that's really driving this under the hood. And then the other thing I want to emphasize is, you can start to think about alternate explanations. Could it be that people in the restricted or unrestricted class just worked a lot harder? And the answer is no, because we can actually track how much time they spent on this. And there is no difference across the 2 groups in terms of how much time they spent on this competition. Okay, so these are the results. I already showed you this. Let me focus on the second one. And here, remember I said we're going to split up skills into general and specific. And here, by general, we're going to look at things that capture statistical problem-solving abilities. And for specific, we're going to capture things that are really around experience with modeling or modeling tools. Now, what we did to get this, it's basically an index where we look at, we ask them 20, 30 different questions, and we aggregate those. Now, you can start to think about how robust are you to these definitions? Well, really robust. We played around with every possible version of this. You can add things, you can remove things. The numbers change a little bit, of course, but the high-level result stays unchanged. So again, I'm not going to show you all that. If you're interested, we have a nice paper that has many pages of appendices. And as we go through the review process, I'm sure we'll add even more pages of appendices. But these results are pretty robust. Perfect. All right, so here, what you can see is that unrestricted and high skill, no effect, right? This is when we're grouping general and specific. There's no heterogeneous effect across this. But as soon as we break out general and specific, we start to see an effect. And this is saying exactly what I said, which is tools are complementary to specific skills, but they're substituting general skills. So in a sense, let me just yeah, I'll give you this intuition here because I think this is really helpful. One of the things we did was we got the best top 3 of each of the tracks to write a blog post on how they solved this problem. And this is a screenshot from some of the work that the person in the restricted group did. Remember, this is the person who didn't have access to advanced machine learning. So what they did was they spent a lot of time on feature engineering and actually plotted the longitude and the latitude of where these pumps were located. And they noticed there's a really interesting nonlinear relationship here, which they then manually codified. Right? That's a lot of work. The unrestricted people just talked about the different models that they used. They talked about XGBoost, LightGBM, CatBoost, and so on and so forth. And that was really interesting to us because it showed that it changed the focus of what people were working on. But we didn't stop there. What we also did was we took the features that this person engineered and we ran it on the best unrestricted model, thinking, okay, maybe there's something there. Maybe there's something with these general skills that's actually really useful and you could have gotten an even further boost. And it turns out that didn't happen. Basically, the new features that were developed by this person in the restricted class didn't really drive any additional predictive accuracy. So that means, at a high level, that these advanced machine learning methodologies are able to codify a lot of this general knowledge that a data science degree will give you, which I think is quite interesting and quite striking. So this is where this is what prompted us to sort of pose this idea that modeling libraries act as this substitution for general skills. But you only really get that advantage if you have the complementary modeling skills. And I'll give you some implications of that. Of course, in the paper, we have like, 20, not 20, but like 5, 6 different mechanisms that we thought could also explain this, and we have data to disprove this. And this is the one that's really sort of the most prominent and prevalent. So let me give you a couple of implications because I'm running out of time. The first one is really around IT productivity. And here, really the big takeaway is, of course, technology and skills are really important. But I think we should think about technology as being broken into the methodologies and the tools that implement this. And this is sort of the first time that people have really tried to study predictive model development as an economic activity. And I think that that's quite interesting, and I think it's really exciting because a lot of the talks I hear these days are very much around the consumption of algorithms, but I think the production is also really interesting and worthwhile studying. And then the final thing, and this I think is really important for policy and sort of the managerial implications is, right, if you think about the types of skills, and we already, Avi got this question, right? We think about the types of skills people are going to need. There's 3 types of skills. You have foundational understanding, which is sort of data literacy, using your data for judgment and judgment for data. You have general skills, which is something you would obtain from a data science degree, right? This is really broad statistical and computer science knowledge. And then you have tool-specific skills, which are really experience with tools for implementing AI and machine learning. And what I think this research is suggesting is you don't really need that general skill. And it turns out that general skill is actually the hardest thing to give people. So what you really need to do is you need to develop tools that codify the general skills, and then you need to train your employees and your population on how to leverage those skills. Exactly like Iavor was saying, we don't all need to know how a computer works, we just need to be able to use it. And that's essentially what this paper is saying, is the implications of skills and tools. And with that, I'm going to stop, and there's a QR code for the paper, and I'm very happy to take some questions. Thank you all so much. Yeah, thanks.
Let's give a round of applause for Iavor. Thanks, Iavor, for a great presentation. I think you've built off of a lot of what the other presentations have provided us today, and that's a really strong understanding of what's going on under the hood in terms of AI development and what are the important components that are involved in predicting success. So thanks a lot for that. Let's start with the audience to see if we have any questions. Don't be shy.
Either this was an amazing talk or a terrible talk. Either I answered all of your questions and no one got anything I said.
Yes.
Okay, a few questions.
Hi, thank you very much for the talk. I'm a data scientist at Choice Hotels International, so I think my job is directly relevant to your talk. And it is true that for us, we don't develop our own algorithm. We kind of just import like XGBoost models or some other models for our prediction models. But I guess the takeaway from your talk, it sounds like, is that we don't really need to understand how like models like XGBoost works. We just need to know how to import it and run it. But I guess the question is, okay, so there are like different models. Like, do data scientists still need some kind of interpret understanding to know which situation is certain model a more appropriate method to solve the problem than other models?
Yeah, I love this question. Thank you for asking that. And this is an important clarification that I wanted to make, that I should have made, and I skipped over because I got too excited. I don't think this is a result for data scientists necessarily. I think this is a result for sort of more broadly people who are not data scientists, right? Because the thing we keep hearing is that AI is going to be a part of your job. You're going to have to interact with it. And necessarily if you want companies to really leverage AI, you can't have a center of excellence where there are two people who understand this and you expect them to transform the whole organization, right? You need to enable and democratize access to AI. And what I think this research is saying is, of course, data scientists are extremely important for the vast majority of problems, but there's going to be a core set of problems which are kind of relatively, potentially easy to automate and to really have people leverage AI who are not experts in that area. And that's what this research, I think, is saying, is that if you're not an expert in that, that's okay. A lot of those expertise are codified by the tools that exist. And that's why I really wanted to underscore that point of using data for judgment and judgment for data, because you need that high-level understanding of, okay, this is this type of problem, we should solve it this way. This is this type of problem, we should solve it that way. You need that baseline understanding, because without that, you have nothing. But I think we are getting to this point where you will be able to leverage algorithms that you may not necessarily deeply understand exactly how they work. Yeah, thank you for that question. It's a really important point. Thank you.
I think we had a question there in the back.
Thanks a lot. That was great. I was just wondering if you could give a bit more context on behind these packages, how much time they're taking. Because obviously in your 48-hour experiment, no one's going to code up that package, right? That's too much of a, potentially too big an ask, or at least from an uninformed perspective. Yeah. So I'm wondering, whereas in a firm, those would be endogenously developed over a longer period, right? People would invest the time in building the package, which is going to be most useful for the sorts of skills. Just wondering if you could comment on, if you had a longer time frame, how things might change.
I think that's a really good question. And I think this kind of comes back to my comment on the ChatGPT one, because that's going to enable you to develop these kind of packages in a few seconds. So I think that when we have those results, I'll be able to give you a much clearer answer. But for now, I think, I think it's a really good question. So I'm not going to attempt to give you a very, very clean answer. So I'm just going to say in like 6 months, I'll have a much better answer for you. But thank you for asking that. I appreciate that.
Anybody else? I did have one. I mean, I've read your paper a couple times. I have like 10 questions here, but I'll leave it to one because I know we have to continue with time constraints. But I was really interested. You talked about the policy implications and the managerial implications for users. I wonder, what are the implications for the actual tool developers? And what implications will they have when generative AI is much more widespread?
I think that's a great question. Huge thank you to Tim, because he's given us so much feedback on this paper, and this paper will not be in the state that it is if it wasn't for his amazing feedback. So thank you. Let me just start there. So I think this paper really emphasizes how important these tools are. And you very often hear questions around, why is a particular methodology more widely spread than another methodology, which may arguably be better? I think the answer is because the tools that implement it are just better, and people like to use tools. So I think this just underscores how valuable, if you're a methods person, how valuable it is that you actually develop implementations and packages to do this. And the interplay with ChatGPT is that it makes it much easier to do that, right? Because you can write your own pretty poor code, then you could go to generative AI and say, fix this and turn this into a really, really nice package, and it will do that for you. So I think it will just sort of lower the barriers, and hopefully it will mean that we start using even better methodologies because we have better tools to implement them.
Great.
Thank you
very much. Next up is Jonathan Timmis, who's going to talk about the implications of capital incentives on cloud, big data, and artificial intelligence.
So thank you very much. As Tim said, unfortunately, Martin Beraja couldn't be here today, so I'm standing at the last minute. And we have a paper joint with Tim, as well as Richard Naylor at the University of Nottingham and Nick Johnston at IEA. And the paper essentially looks at capital incentives, so incentives for tangible investments like tax breaks, and how that affects the diffusion of cloud and big data and AI technologies in the UK. So traditionally, back in the day, before we started talking about AI and whatnot, people thought of digital adoption in terms of, buying hardware and software, sort of 10 years back, and that's what people thought of in terms of digitalization, buying PCs, buying, servers, this sort of thing. And a lot of policies around the world incentivize tangible investments in these sort of tangible hardware and software. But then relatively recently, there's been several changes, such as the arrival of cloud computing, where instead of having to buy your own servers and so on, you can pay for a service through the cloud. Amazon buys the servers, you use Amazon's servers, and you just access them through the internet, and you pay for the service. And there's several papers find that use of the cloud is complementary to big data and AI. You need the ability to store and process lots of data on demand, which is often cheaper and more flexible through the cloud. So this paper essentially looks at a UK tax incentive, which incentivizes tangible capital investment, not just IT, all types of capital investment, but it includes IT as one of those incentivized investments. And then we look at when this tax incentive is imposed and subsequently changes, what happens to firms in the UK in terms of not only their investment in tangible assets, but more interestingly, what happens to their likelihood of adopting cloud or big data or AI. So I briefly touched on what is cloud computing. So, and the key thing here is it changes the way firms access IT. So previously you had this fixed IT capital. If you wanted to store and process a lot of data, you had to buy a lot of servers, and it was going to cost a lot of money. Nowadays, you can buy these services through the cloud. You still need basic ways to access the cloud. You still need some infrastructure, but they're not. But you don't need to necessarily pay for all these servers yourself. You can access these systems through the cloud. And so, starting from 2006, when AWS launched in the US, you can access all these services through the internet. So you have this sort of, this is the image here, the trade-off of an IT department installing all your own machines versus accessing a server farm through the internet. And why does this matter? Well, Tim and I have done some other papers before on cloud computing, and as you can imagine, the shift from a fixed cost of buying your own servers to the cloud, which is a variable, flexible cost, is particularly helpful for startups and SMEs. They're often capital constrained, and so these types of firms particularly gain from cloud computing. So we have some papers, other people have papers on the US showing that this particular SMEs and startups particularly gain from cloud computing. And as I said, this is a complement to the use of big data and AI. You need large amounts of data very often to train your algorithms, which needs large storage, large processing. And so several papers, not mine this time, have shown the complementarities between cloud, big data, and AI. So I mentioned briefly the policy we look at. So every OECD country has some sort of tangible capital incentive. at the moment. And these, can cover, subsidies or, tax rebates and various sorts of related programs. But every OECD country has some sort of tangible capital incentive, and very, very rarely do these cover IT services. So essentially, you're subsidizing buying your own machines and buying a server, and you're not subsidizing cloud. That's the whole idea of this paper. And what happens if you subsidize one part of this trade-off? So we take advantage of this UK capital incentive, which was introduced just after the financial crisis, and it's been modified several times thereafter, and now is actually a very large incentive that's got bigger and bigger most years. I think it's currently £1 million per year, which is quite big. And so the idea is if your own IT investment and cloud services are partial substitutes, then if you incentivize buying your own machines and servers, then you may be slowing down potentially the cloud. So the data we use is from the UK Office for National Statistics, essentially the Census Bureau of the UK. It's, in theory, representative data of almost all sectors and firms above 10 employees. We combine two main data sets. One is the annual business survey, which contains data on investment and other measures of firm performance and so on. And that's available annually. And then we combine this with the e-commerce survey, which is the same data that Flavio was mentioning earlier. Other European countries have a similar data. Essentially, this is the UK version of what Flavio was talking about for other countries. And it surveys technology use in firms. So we have cloud and big data and AI available, but only for certain years. And so what we do is assume in 2007 the use of these technologies was zero, which is what we've done in other papers. Before the cloud was launched in the UK, you can safely assume adoption was zero. So our baseline analysis focuses on 2007 to 2013, but for some of the results involving big data and AI, we go to more recent periods, and we've done robustness checks of all different combinations of time periods. The results don't really change what we do. So this is the summary statistics of the firms we have in the matched data across all the years. So 34% of the firms have cloud of any type, but then we actually measure the particular use of cloud. So what cloud service are you buying? Is it cloud to be able to store your data, like data storage services? Is it cloud processing power, like you're buying? Or even simple things like using the cloud to host your email? Nothing terribly sophisticated necessarily. And so we measure these different cloud types. 26% of firms use big data, but only 1% use AI. It's very, very rare in the periods we look at. So we use the investment variable will be relevant because this determines eligibility for this tax incentive, which is why I mention it here. We'll see later that some of the thresholds for eligibility for this tax incentive are 50,000 in some years, 250,000 in others, and I mentioned 1 million in the most recent year. So just to give you an idea of how many firms are we talking about, the £50,000 incentive, which is the first year it's introduced, represents about 20% of our firms. So we have a reasonable number of treated firms versus control. So the allowance itself was introduced in April 2008 and then changed several times. All types of tangible capital was eligible apart from land and buildings. So vehicles, machinery, IT capital, in our case as well. So everything apart from land and buildings is eligible. And what you can do is a firm can deduct the investment up to this threshold from their pre-tax profits. So essentially you get a tax break on investment up to that amount each year. So you can spend 50,000 per year and get your tax back, your corporate tax rate back on that 50,000 in the first year. The actual calculation of the allowance is actually quite complicated. I'm not going to go into it, but you'll notice it changes several times and in different months. Sometimes it's March, sometimes it's December. And the actual allowance per firm depends on when your actual financial year is. So a firm having January to December financial year gets a different allowance to a firm having, April to March. And so we have information on that. We know the exact financial year ends of every firm. And so based on this table, we can calculate the exact allowance every firm is eligible for that financial year. Where we follow the literature, we basically similar to the R&D tax incentive literature. There's quite a few papers on that, where you get a similar sort of system of, a tax break on R&D up to a certain amount sometimes. And we follow that literature, and I've listed some of these papers. And the idea is that firms with investment below these thresholds I've just mentioned in the previous table, they essentially have a lower marginal cost of additional investment, because every extra pound they invest up to that threshold, they get the tax back. Our estimation, we look at changes over time. So we look at within firm changes, and we look at the changes in this allowance, so both when it's imposed and changes over time. So when the threshold goes up, new firms are suddenly beneath this threshold and incentivized to invest more. If they invest more, they get to the tax back. Whereas previously, if you were above the threshold, every extra pound, you don't get any rebate. So we use the changes in this threshold over time to determine which firms get the reduction in their marginal tax rate, and therefore who's incentivized to invest more. I've said investment determines your eligibility up to this threshold, and obviously investment is an outcome. So it's the same thing with the R&D literature. You get a rebate up to a certain amount on your R&D, and then they look at how does that affect R&D. So the way we get around that is we used lagged investment before the AIA policy existed in 2005-06, essentially to determine eligibility, like an instrument, essentially. And that's a common practice in this R&D literature. So then you use this lagged investment, you compare it to these thresholds that are changing over time, and then you see what happens to these firms that suddenly, because the threshold increases, they suddenly get a reduction in their marginal costs of investment. Sorry, it's a bit tricky to explain this. I'm not a tax expert either. So this is the regression equation. I've said it's within firm estimation. It's essentially a difference in difference estimation, where we, as I said, we use these changes in this AIA threshold to determine who gets treated. The outcomes are investment, is what happens to investment of various kinds, and then what we're more interested in, the cloud data and AI outcomes. We have the firm and year fixed effects, hence the within firm estimation. And we define the treatment group, if the treatment dummy to be equal to 1 if the lagged investment measured before in 2006-07, as I said, is less than or equal to this AI threshold in any previous year. And we add some firm controls, but it doesn't really make any difference, the controls. So I will show some results. Because investment is available annually, we can do a nice event study plot. So this is if you're following the literature, there's lots of modern developments in differences and event study estimation. We follow one of them here. I won't go into details, you can ask me about it later, but essentially it's an event study where it compares people who got this, became eligible for this tax incentive compared to firms that haven't ever been eligible. And you can see around the time of the AIA change, there's no real pre-trend, so it seems like the firms that subsequently became eligible and never became eligible behave similarly. Their investment is pretty similar, but then you see a marked increase after they get eligible for this tax incentive, which is what you'd expect. It's what the policy is meant to do. It's meant to stimulate investment, so it does stimulate investment. The rest of the results will all be in regression tables because, as I said, we don't have the technology variables every year, so we can't plot this event study graphs in the same way. But we'll start with investment first and then go on to technology. So as I just showed in the graph, this first column shows the same thing, essentially, that investment goes up for the firms that become eligible for this tax incentive. And then we look at the different types of investment. Because if you remember, land and buildings wasn't eligible, so we're hoping that we don't see an increase in investment in land and buildings because it's not eligible. Unfortunately, we don't. We do see it for the other types, plant and machinery, vehicles, IT software. The observations are a little lower for some of these because they're not available in every year. But the policy works as it would expect. It was designed to stimulate tangible investment. It stimulates tangible investment. But what happens for these same firms in terms of their technology usage? So if you think, as I said, investment in servers and IT investment is a partial substitute for cloud, then you would expect these same firms who spend more on their own IT to probably spend less on cloud, or less likely to adopt cloud. Sorry, this is a dummy variable. And you can see that quite strongly here. These treated firms are 16%, well, 16.5% less likely to adopt the cloud. These are big numbers. And it's particularly the types of cloud that is useful for AI and big data. It's the cloud for storing data, and it's the cloud for processing data. We don't see anything for hosting email on the cloud. So given that we find that firms are less likely to adopt the cloud, and it's particularly the types of cloud relevant for AI and big data, it might come as well, I'll go back to that. No big surprise that when we look at what happens to the use of big data or AI within firms, this also slows down. So they're much less likely to use big data, they're much less likely to use machine learning, but we don't really see anything for natural language processing. I'll just go back to the previous slide. So then we also do lots of robustness checks and looking at which types of firms. I'll just present one here where we look at firm size distribution. Because you might remember when I started, I said cloud's particularly beneficial for SMEs and young firms because they're capital constrained, and so they like this variable cost rather than a sunk cost. So we looked at which firms in particular is their cloud adoption slowed. And you can see it's particularly these SMEs. So the firms that have the most to gain from cloud are the most incentivized not to use it because of the capital incentive policy. Which is, and again, these figures are huge. If you look at the small firms and you add the two coefficients up, that's more than 30% less likely to adopt cloud. So these are really big numbers. So just to sum up, and then I'm very happy to take any questions. So we find that as a background, every OECD economy has some tangible capital investment incentive program. I mentioned one here in the UK. The UK had an earlier one that was specific just for IT for earlier years. So these are very common, and these often include IT as part of tangible investments. But in general, businesses are shifting towards services and towards intangibles. And so these policies that were designed for an era of tangible investment maybe are not so appropriate or need to be updated for an era of services and intangibles, because we find that these capital incentives, whilst they work as intended, stimulating tangible investment, they slow down cloud adoption, they slow down big data, they slow down AI, exactly for the firms that have the most to gain. So we think that policies designed sort of with an old school view of IT maybe need to be a bit updated. And I might say that some countries have actually started changing their incentive programs to include IT services as eligible, which is one of the obvious ways of, I guess, of not leading to this substitution. Thank you very much.
Thank you very much, John. I think that was a nice look at the implications for policy and how it may be slowing down the diffusion of these emerging technologies. Do we have any questions from the audience?
Could you say something about the design of solutions to this that would incentivize investment in the cloud, and in particular, any incentives for hybrid systems that include both the capital investment in hardware and cloud services?
Yeah, so, I mean, I guess the rationale for these policies is that, firms are capital constrained, and you're trying to correct that market failure of paying for sunk costs. If cloud is flexible, then I guess the first point is that ignoring this substitution thing, is there a market failure? If it's really a flexible cost, what's the market failure that's stopping small firms adopt? I mean, I guess that's one point to start, that the market failures may be different. But there's definitely problems in terms of this inadvertent substitution you're causing and slowing down So I don't know the full details, but I do know that some countries, I think Spain, for instance, I don't know if you know any others, Tim, but include cloud expenditures as part of these incentives. So you can invest in a server, or you could spend the money buying cloud services, and that would also receive the tax break. So essentially, you incentivize both.
Any other questions? I guess if I would build off of Brian's question, I'd ask, should we just scrap capital incentives? Are they completely out of date, or do we need sort of a hybrid policy environment that encourages both firms to adopt in, say, hardware such as computers, laptops, and mobile phones, while at the same time encouraging them to substitute away from a physical infrastructure of digital technology within the firm to ICT services?
Yeah, I mean, it's even a broader point, because, we already incentivize some types of intangibles like R&D, don't we? But we don't incentivize other things like data or whatever, other types of intangibles. Or sometimes you incentivize skills training, potentially as well. So there's already a bit of a mix, and so it depends what unless you don't think there's spillovers from data, that would be the argument, I guess, not to incentivize it. But I think if you made the argument that most of these intangibles do have spillovers, then it seems odd to be cherry picking some and not others.
Anybody else? Well, great. Oh, yes, please.
Hi, thank you. Quick question. So, the cloud has been around for a while now, and it's very mature. So, I'm surprised that there's still benefit from these tax breaks rather than moving all the data centers to the cloud and saving on hardware cost. Is that still the case?
So we have looked at it through time. I've said that choosing your end period doesn't change too much. We have tried to look at the different changes over time. It's difficult to look over time because you have both time is changing and the maturity of cloud, and the investment allowance is changing. So it's going up and up and up. So the treated firms are getting bigger and bigger. So it's not necessarily a fair comparison to say, oh, what happened when it first came in versus the most recent increase, and therefore, make a clear comparison. But the effects that we've seen are generally stronger at the earlier periods, which maybe is to your point, or maybe is also because of these are the smallest treated firms, and they're the most capital constrained. So it could be either point. It's hard to discern, but good question.
Well, if there's no more questions, I'll say, why don't we transition to lunch for those that are in person in the room, and for those that are online, we will be back here at 1 p.m. Eastern Time. Thank you very much.